Okay, cool. Right, so absolutely need to look at the screen of the people. Anyway, okay, so yeah, welcome to today's session, which is about climate model ensembles, variability, like climate variability, and uncertainty in projections of extremes, so like spread in projections. So this is mostly a practical session, but I'll do like an introduction sort of mini lecture to start with. Okay, so yeah, if you look in something like the IPCC report, you often find, can you see my mouse on the, I can see it on the, let me do a pointer. Yeah, we can see it. Okay, often you'll find this kind of graph. So this is showing projections of global temperature change from 1950 to the end of the century. And you see that this is from CICERO climate models, and you get this spread, like particularly at the end of the century. And this kind of spread comes from a number of different sources. It can be different choices of scenario. So in this case, this is important, like whether it's a high emission scenario, whether it's a low emission scenario. So that gives a big difference. But then there's also other sources of spread. So you can see from the two of these lines, there's also displayed a kind of shading. And this is showing the spread across different climate models. So the choice of model contributes to spread in projections, and also internal variability of the climate system can also cause spread. So yeah, there's different sources of spread, so differences in models, different scenarios, and also internal climate variability. And the importance of these different sources depends on what you're looking at. So the variable, the spatial scale, the time frame. So here, this is precipitation, so it's the same graph basically as the temperature one, but you see here there's much more overlap between the scenarios, so the shading is kind of on top of each other. So the precipitation model differences and internal variability are more important than they were for temperature compared to choice of scenario. So it depends if you're looking, say, at the global mean, or if you're looking at a grid cell, then the relative importance of these things changes. And you can explore this for different types of climate model ensemble. So just a bit of recap from the previous first workshop. An ensemble is a group of climate model simulations running the same experiment, and there's different types. There's initial conditions ensembles, where you have the same model and you run it each time with slightly different initial conditions. So you start, so all the ensemble members start almost from the same point, but with slight differences, and then over time they diverge, and each one has its own phase of internal variability due to the chaotic nature of the atmosphere. And the internal variability can come from things like the El Nino Southern Oscillation, or the North Atlantic Oscillation, or there's also things operating on longer time scales like the Atlantic Meridional the Atlantic multi-decadal oscillation, which is like, say, 60-year cycle or something like that. And also the weather is variability on short time scales. So you can have large initial conditions ensembles, which have, say, 50 to 100 members. And some examples are the NPI Grand Ensemble, the CANI SM5 Large Ensemble, which is one we'll be using in the practical. And there's also a climateprediction.net, where there's thousands of members, which is run on volunteers' computers. And so these kind of ensembles are useful for exploring internal variability, so quantifying the variability, getting good statistics, trying to understand it, and also looking at how much difference internal variability can make when you're looking at projections, say the next 10 years, 20 years, 50 years. whatever. But you can also average across all the different members, and that allows you to get a kind of noise-free estimate, so the variability cancels out, and then you can see more clearly the response to greenhouse gases. No worries. Yes. Okay, and then you also have multi-model ensembles like CMIP5, CMIP6, and where different models run the same experiments, so running the future with the standard scenarios, the SSPs, or the historical period with observed records of greenhouse gases, aerosols, volcanoes, and so on. And then you can explore what difference using a different model makes. Generally, each model only contributes a few ensemble members. In CMIP5, they tend to contribute 1 to 10. For example, for CMIP6, there's some larger ensembles. And yes, as I said, this is useful for exploring model uncertainty. So this is just the same diagram as before, but for multi-models, so each different color is a different model. So you'll get differences partly due to choice of model, and also they still have their own internal variability, which also contributes to making differences between them. And then just a very quick note about perturbed physics ensembles, since this is also a type of ensemble, but we're not going to use them today. But for these ones, you can explore the effects of changing uncertain parameters within a plausible range. So maybe you don't know the albedo of sea ice, for example, but you know it's probably between this value and this value. So you can run the model with different values of this parameter and see how much difference it makes. So in this case, you have 3 different sets of parameters with the different colors. And here, actually, it does make quite a big difference. You can see that, that they're quite separate, the different groups of simulations, and they still have internal variability, but maybe for some parameters, it might make less difference. Maybe they're all on top of each other. Okay, so here's an example of what you can do with the large initial conditions ensembles. So this is using a 40-member ensemble of the CCSM3 model. So it's an initial conditions ensemble. So the members only differ in terms of their internal variability. And this is taken by a paper from Clara Deza. It's looking at 55-year winter temperature trends over North America. And so you can see for the ensemble mean, this kind of classic pattern of warming, which is amplified in the Arctic. But you can also look at different ensemble members to see how much they differ from each other because of internal variability. So this is the ensemble member with the warmest trend over North America and the coolest one. So you can see this one has a bigger area of warming, which spreads further south, whereas this one actually has a cooling. So these are the most extreme members. Most of the members would be in between that. But it's just to show that internal variability can sometimes enhance warming and sometimes it can offset it for a while. And then they also go on to show how the role of internal variability depends where you are, so in the tropics or in the subtropics or in the mid-latitudes. So you see these time series on the right. So for example, Seattle has a lot of internal variability. And then they plotted the ensemble member with the biggest trend and the smallest trend. And you can see there's quite a bit of difference between the two of them. So this one has quite a strong warming and this one's kind of flat. And the difference between them is due to internal variability, and most of the ensemble members would be somewhere in the middle. And then in Mexico, for example, then there's a bit less variability, and now the member with the most warming, the least, is actually quite similar. And also they looked at spatial scale. So over the scale of the United States, internal variability is still pretty important, and you can still get quite a big difference between 55-year trends between ensemble members. But if you look at the global scale, then actually there's very little difference between the member with the most warming and the least, and you see that there's not so much variability, although there is some. So we're actually going to, I mean, if we get that far, we will try to do these kind of maps for Europe and for the Balkans to see how much difference you get between the member with the most warming and the least. Okay, and this is just going back to multi-model ensembles, just showing annual mean surface air temperature for the end of the century for RCP 4.5, just showing differences between models. So you see that they, yeah, you see that they agree on the general patterns, like you have warming, it's particularly big over the land and over the Arctic, and then you have different, but you also have some differences between the models, and in this case it's mostly coming from model differences rather than internal variability, because you can compare different versions of the same model, like this one, for example, Access 1.0 and 1.3, they look very similar, or these two BCC, CCSM models look very similar. So I think that the differences we see between all the different panels is due to model differences rather than internal variability. So basically how important these different factors are depends on how you look at things as well as what you're looking at them, etc. Okay, so coming back to these plots I showed at the beginning, which is just showing projections and global temperature change for those who are not weren't here, and for global land precipitation. I was just saying that you get spread in projections as you go through time, and that it can come from different sources, like choice of scenario, choice of model, and also internal variability of the climate system. And the relative importance of those things depends on what you're looking at, like the variable, the spatial scale, like global or like local scale, and something else, the scenario. Yeah. Okay, so you can, so some people have broken down these particular plots into the sources of uncertainty, like this. So you see it's kind of the same thing, but now split into different categories. So the green, so this is the temperature, decadal mean temperature. So you have in green the scenario uncertainty, and blue is the model uncertainty, and then orange is internal variability. And so you can see that at the end of the century, scenario uncertainty is the main source of spread in projections, followed by model uncertainty, and internal variability is not very important. But in the near term, well, you have less spread overall, but proportionally now model uncertainty is the most important. Internal variability is also fairly important, and scenario doesn't really make much difference over the next 10 years, for example, or 20 years. And then this is the same, but for precipitation, so decadal mean precipitation. So in this case, now actually model choice is the biggest source of spread, and scenario is second, and then internal variability. So yeah, it depends a bit on the variable you're looking at. And then this is just a different way of looking at the same thing, just displayed differently. So now it's the proportion of the spread which is coming from the different sources. So again, so this is global mean decadal mean temperature, and at the end of the century, most of the spread is coming from choice of scenario, followed by choice of model, and then internal variability is tiny. I don't know if you can even see it, but it's just really small bit at the bottom. But at the beginning, so this is zooming into the first 20 years. Here you see scenario doesn't make so much difference, and the other two are more important. And then if you look, so this is decadal mean, but if you look at annual mean, then the orange, that's internal variability, its contribution gets bigger. And if you look instead of at the globe, you look at North America, then internal variability gets proportionally bigger contribution to the spread. So basically, yeah, it depends what you look at and the spatial scale and the temperature scale. So that was it for the lecture part. Feel free to ask questions or whatever. Otherwise I'll just go on to say what we're doing. today. I don't see the chat, by the way. Is someone will tell me if this.
We'll track now trouble with the internet connection. Is there any comments to chat?
I don't see anyone here. Okay. Okay, so let's move on to today's practical session. So we're going to explore this uncertainty or spread in climate model projections of extreme indices. So we're going to see how the relative importance of these sources of uncertainty, so internal variability, choice of scenario, and choice of model, how does the relative importance of those depend on the variable you're looking at, like precipitation versus temperature-based indices, the spatial extent, so the global mean versus European mean versus Balkans mean versus Novi grid cell, and then also the time period, so how much difference does it make if we look at a trend over the next 30 years compared to the next 80 years? And we can think about when does it make sense to use which kind of model ensemble. So we'll look at two indices. So there's TXX, which is the annual maximum of daily maximum temperature. So in other words, the hottest day of the year, or the temperature of the hottest day of the year. And then RX1 day is the amount of rain that is on the wettest day of the year. And we'll look at three ensembles. So there's CANI-SM5 large ensemble, which has 50 members for 4 different scenarios. So this model has a high climate sensitivity. So that means for a doubling of CO2, it warms a lot. And then MIROC6 is another large ensemble with 50 members, which has data for 2 scenarios, and this one has a lower climate sensitivity, so it doesn't warm as much for a doubling of CO2. And then we have CMIP6, so that's the multi-model ensemble. And so for this, I have 1 member each from 21 different models, all 4 SSPs, so we can compare results to the large ensembles. And we'll produce a lot of plots, hopefully. So some of them look like this. So this is, for example, this is CANI-SM5 RX1 day at the global scale, and you have the different scenarios, and you can see how overlapping or not overlapping the scenarios are, and like how much spread there is. And you also see there's all this internal variability, like all the wiggles, and you can compare it to the same from CMIP6. So in this case, you see that for SSP 585, for example, you cover a much bigger range of values when you use CMIP6, which suggests that if we were only using CANI-SM5 for our climate projections, we would be overconfident in the results. So we can have a look at that kind of thing. And we can also see what the effect of smoothing is. So when you look in the future, you rarely look at just 1 year, you tend to look at a time period like 20 years. 30-year average, so we can smooth the time series with a 21-year running average, just to see what happens. And we can also produce some histograms like this. So here I have so this is CANI-SM5 on top, and then MIROC6, and then CMIP6. And so for each ensemble member, we'll calculate the trend, so in this case, the Balkans, and then we plot it as histograms. So in this case, if you look at the blue one, SSP126, you see most ensemble members are showing a warming trend over the next 30 years, but a couple of them are actually showing cooling, and that spread is due to internal variability. And then you also have differences between scenarios, so you can see how much spread there is, how much the scenarios overlap with each other, and how the 3 different ensembles compare. And then we'll also plot it for other regions and time periods and see what happens. And then the last thing, if we get that far, and it doesn't matter if we don't, because I have all the plots already made, so we can just look at them and discuss. But yeah, this is like that paper I showed before, the one by Clara Dessa, where we can plot the ensemble member with the biggest trend and the smallest trend over the next 30 years and over the next 80 years. So, hi Rob. And so this is, we're not actually looking at TNN, that's the coldest temperature of the year, but I just put it here anyway because it was in the version I did for the senior research. But yeah, in this one you see there's cooling in this member and there's strong warming in this member. So there's actually quite a big difference between different members because of internal variability. Whereas if you look at an 80-year timescale, then actually the member with the biggest and smallest trends are pretty similar. So that's it. But the secondary aim is to further develop programming skills. So if everything goes okay, we will start with processing some climate model data. So the idea is basically that when you do climate science stuff, often you have to download data from ESGF for CMIP6 or climate models or whatever, and then you have to process it to get what you want from it. But so we're not downloading anything from ESGF, but we have some data which is in quite a similar format to what you get from ESGF. So we'll see how you can use BASH with CDO and NCO to loop through all the files and get what you want from it. So it's quite useful. I learned to do it a few years ago and it's really made me more efficient because before I was just doing something, yeah, really inefficient. And then we'll use Python to make the plots. Oh yes, and I left you a challenge. So I've provided scripts for 2 of the ensembles, so CANI-SM5 and CMIP6, and I left gaps for MIROC6. So if you want a challenge, then you can try to do the parts of the scripts for MIROC6, which is just a case of kind of copy, paste, and then edit a bit to fit MIROC6. But I did also make scripts with MIROC6, so you can also look at them if you need inspiration. Okay, so that was that for the lecture part. Did Brianna? Do we go straight on to the practical?
If you like to have 5-minute break and then go to the practical, so that everyone has everything ready on the computer, so find the data that's looking down on the one side, and then we can go.
Okay.
Yeah. It's okay to have 5-minute break.
Perhaps please somebody.
Oh,
Okay, and questions.
and then the revert will make the sorry.
Okay, no worries. Okay then, right. Okay, so you should have found an instruction sheet like this in the folder. So yeah, I guess the first bit is basically what I said already. So we're exploring uncertainty, so spread and climate model projections of extreme indices using different types of climate model ensembles. So we'll look at how the importance of the different sources of uncertainty depends on the choice of model, choice of scenario, and internal variability, how it depends on the variable you're looking at and the spatial scale, so global mean, European mean, Balkans mean, and Novi grid cell, and also whether you're looking at a 30-year trend or an 80-year trend. So I said this already, we're looking at CANI-SM5 and MIROC6 large ensembles, and also CMIP6. And yep, I said that. And I said this as well, just to note that there's numbering of the ensembles. So in climate model data, you have this numbering of the different ensemble members, which looks like this kind of thing, like R1, I1, P1, F1. And so in the scripts, we have to kind of deal with that. So for CANI-SM5, for example, the R number goes from 1 to 25, like R1, R2, R3, R4, R5, etc. And also this P number changes, which is the physics version, so between 1 and 2, but we'll see this in the script. And MIROC 6 is simpler, just the R number changes between 1 and 50, and that's it. And for CMIP 6, we only use R1 for each of the models. Okay, so then we'll start by doing this processing with the bash script. So I hope that it will work, but if it doesn't, I have some backup data, so it's okay. So the script is called script 1 processing CANI-SM5. I think if you're here in this computer room, now actually you need to use the version which says with NCO on the end, because I think the other one won't work. Hang on, I just, no. Okay, so I'll show you, I'll open the script and I'll show you what's, yeah, I'll talk through the script so you can see what it's doing. But for anybody who's at home following this, so basically this bit is saying, okay, run the script, but there's also this one point where the script might not work if you're using the script 1 processing CANI-SM5, which is the CDA field mean command. Sometimes it gives missing values. So if you've looked at the test script, then you'll know whether or not it's going to work for you. But you can have, if you didn't, then you can try running it and have a look at the file and see if it has missing values or not. And if it does, then we use an alternative, which is just with NCO version. So yes, and let me show you the script. I just wait a second. Okay. Okay, so I just tried to explain what this script is doing so you hopefully understand what's going on, so it's not just a black box. So anyway, this is a bash script, so it starts with this hash exclamation mark bin bash. I don't know if everyone can see my mouse. Yes. Can you see it through Zoom as well? Okay.
Sorry, are we recording this?
Yes. Yes. The sandwiches look good, by the way, for anybody not here. Okay, so yeah, you start with the spin bash thing, which tells the computer that this is a bash script, and then you can load any modules you need, but this might be different for you guys, and Benita, who's the expert at this part.
So the users who use Windows operating system have to do some Linux emulation, and we use here at our computer room Serbia. So you can start. You have a short desktop Serbia and Serbia terminal, Serbia 64 terminal. And the first step is to change the working directory to the folder where we keep the script. So now we use CD, like change directory, the CD, space, B is the name of the partition, B, yes, and enter. Now with the build command, you will get the contents of the data. So Evo da pronađete folder u kojem se nalaze vaše slike. Ja vam predlažem da prekopirate ono što stoji u workshop 3. U jedan folder sa što kraćim nazivom, da ne biste svaki put morali copy-paste, nego jednostavno stavite na neki. So you rename your folder to have the shortest possible being. I na dve partici, dakle, samo na dve partici bude dve, što mora staviti. I onda radim slika. The first batch split is Carley's longer, shorter. Carley's and 5 or with NCO?
With NCO.
Yes, we are starting with 6 and they are navigating to that positive.
I know what you want to we need to put the script into the directory where the NC files are. And then am I right?
Yeah, but don't execute it just yet. But...
Okay, we just try it. Okay. That what is that? I have to speak. They did this for this analysis.
The amplifiers have to be in the same level directory for the sum order, or
no, because you can change the path in the script. I'm going to say that.
Oh yeah, okay. We want to show them how to trigger the path. I open then the script in both tags. Which tags? Is it the same? It's not.
It would be.
Yeah, okay. Yes,
yes, we managed to.
Okay, right. Yeah, if I could have your attention, please. So I'm just going to explain what the script is doing. So I've got the same version as you now. So the version with NCO. So basically what the script does, so for each member of the CANIASM-5 large ensemble, it calculates the spatial mean for the globe and for Europe and for the Balkans, and it extracts the time series for the Novi side grid cell. So it does it for all 4 scenarios and for the 2 ETCCDI indices. So that's the TXX and the RX1 day. They are ETCCDI indices, which is a wider set of indices. We don't have to worry about that. So yeah, the script uses the data which you will have found in the data to download /CANIASM-5 folder. And so we'll adjust the paths in the script so it points to the data. And then this is what I said before about the ensemble member numbering, so I skipped that bit. But yes, I hope that the script can be a useful kind of example or template in case you need to do this in the future. But yeah, so the first thing is these are the paths that you have to modify to point to the data. So the first one, this F equals blah, blah, blah. So this is the directory where the model data is stored. So you just change that to where your data is stored. And then dest is where you want the output data to go. So you might need to create a directory for the data to go in, which is produced. And then I also set up a temporary folder for temporary files. So we'll do a number of loops. So this for blah, blah, blah do is a loop in Bash. So in this case, at the beginning, I set up a list of the different scenarios and the different ETCCDI indices, which we can loop over. So this is a loop over the ETCCDI indices. So for E in the dollar list thingy do, this basically tells it to loop over the ETCCDI indices. So for the first loop, the value will be TXX. The second loop, the value of E will be RX1 day. And this is another loop, but this time over the different ensemble members. So on the first loop, R is 1, and then it's 2, and so on until 25. And then we do the same for P between 1 and 2. And here I'm just calculating the mean of the reference period because I want everything to be as anomalies. So I use CDO for this. So here I've combined two different commands together. So cell year is selecting the time period that I want, so 1981 to 2010. And this time mean does the mean over the years that I selected. And here you'll see that I've got all this notation with these dollars and letters and stuff. So this is where I'm making use of the information in the loop. So for example, here I have dollar curly brackets E, and that means insert the value of E. So the first time it will be TXX. So it's these, and then the second time it will be RX1 day. And then I can do the same with the R number. I insert the value here and with the P number. And so that's just a way of, so you don't have to write out every time all the different combinations of the files, which would obviously take up a lot of space and take up a lot of time. So you just, instead you put in these dollar whatever, which inserts the value of a variable into your file name. Okay, so yes, so that I'm making the reference period mean in this line, and then I loop through the scenarios in the same way. Then I'm just making the data into anomalies relative to the reference period mean in this one. So CDO sub is just subtract. And then this is the bit where I'm making a spatial average. So this is, instead of using CDO field mean, which doesn't work, we use NCO instead. So we have to define some weights. So basically the grid cells at the equator are bigger than the ones at the pole. So you need to weight them to take that into account. So this is just defining some latitude weights and then applying the weights whilst making a spatial average. In this case, this is for the global. And then for the Balkans, first of all, we have to select the box over the Balkans. So CDO cell long lat box is, you just put in the latitudes and longitudes that you want, and it selects this box. And then I do the weighted spatial average, again, as before. This is the same for Europe, so it's really the same thing. And then the last one is selecting the Novi grid box. So for this, you can actually use the CDO remap NN, which just selects the grid box, which is closest to the longitude and latitude you want. So this is the longitude and latitude of Novosad. And then I just delete the temporary files, and you have to close off all the loops by writing done. And that's it really. So all you need to do is modify these paths to suit where your data is and where you want the output data to go. And then hopefully you can run the script.
Yes.
How we can do that. So this is the same thing, but for CMIP 6. And you see here, I've made a list of all the different model names. And I put this in the loop. So instead of looping over ensemble members like R1, R2, R3, blah, 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 instead you can make a list of all the model names and then I put it here. This for M in $CMIP6 list, semicolon do. So that's another way you can do it. And for MIROC6, it was very similar to with CANI SM5. So just looping over the R numbers 1 to 50. So yeah. So yeah, we can move on to the Python bit. Let me just think a second. Oh no, that's Rob's. Oh, I'm not sharing my screen either. Sorry.
I have a request on the chat to share the screen.
Yeah, sorry, I forgot. Screen share. Okay, sorry, I better say that again for the people online. So I was just saying that for these scripts, you can also make a list of, say, for example, model names like I have in this one, the CMIP6 list, and I can make a loop over those, which I'm doing here, but in CMIP6 list, semicolon do. So for CMIP6, I did that instead of looping over all the R numbers. Yes, and then I was just saying that the one for the script for MIROC6 is pretty much the same as the one for CANI SM5. So this is the MIROC6 script, and the difference is just that I'm looping over R numbers 1 to 50, and I don't need to loop over the P numbers. And so that was it really, just to say how it differs or is the same. So then I was going to move on to the Python part. Okay, so the idea is to read in the time series that we just calculated into Python. So we read them into Python, we store them in an array, which is like a multi-dimensional table, and then save them as a .npy file. And the reason for doing that was just that it's quicker to load this Python file than to read in all these netcdf files over and over again when we want to use it later. So for the sake of simplicity, I was thinking we could use the time series that I already calculated, which you'll find in this Plan B data folder. The reason for that being that when I tried to rerun all the scripts using the data I had just calculated from the script you just ran, it didn't work anymore for some reason. So I think it's simpler to just take the data that I have in this Plan B data folder, because then I know it works, but it should in principle be the same as what you just calculated, but also it has the other two ensembles, so MIROC6 and CMIP6 data in there as well. And so to run it, well, assuming it works the same on these computers as it does for me, you type Python -I name a script.py.
Yes,
and the -I just makes you end up in an interactive session, which can be useful if you want to do debugging, like try to work out what went wrong. But you can also run it without the -I. And then to leave the interactive session, you press Ctrl-D. So maybe I just show you the script. Just a second. So it's this script to read ensembles.py. And then I was just going to go through and explain what's happening. If anyone's listening. Sorry, it's okay. I take it. Okay, I was just going to explain what the script is doing. So basically, you start off by loading the libraries that you need, and then so basically we're going to do some loops like we did before with the bash script in order to read in all the different data files. So in Python, you do loops slightly differently to in bash. It just has a different way of writing things. But the principle is the same. So I set up some lists like I did before in Bash. So for the ETCCGI indices, for the scenarios and for the regions, and for the EC, I have to write it slightly differently, like with commas and whatever. Then here I'm making an empty array to store the data in. So it's like a big table. Oh, hang on, Margaret's saying that we need to let her in. Hang on, let me let her in. Hopefully that works. Okay, so yeah, I set up this empty table and it's size 4 regions, 4 scenarios, 2 indices, 50 ensemble members, and 86 years. That's the size of this table. And then I fill it with missing values, and which we will overwrite. And then here's the directory to the data. So you might have to change that to the data in the Plan B folder. And then here I'm doing some loops like I did in Bash, but the syntax is a bit different. So here I'm looping over the different ETCCGI indices. So for EI dex, I just called it that, comma E in enumerate ETCCGI list, colon. So basically when I go through this loop, say E takes on the value of the ETCCGI index. So the first time it will be TXX, and then it will be RX one day. And this EI dex, that's a counter. So it starts on 0, and then it's 1, and then it's 2. And then I'm looping through the regions and the scenarios, and then the ensemble members. So here I called it M instead of R. And so to loop through numbers in Python, you actually have to loop. You have to carry on 1 more than what you need. So we have 25, so I need to tell it to go to 26. Don't ask me why. I don't know. And then the same for the P numbers. And this is basically making a file name, like before we had the dollar, curly brackets, whatever. In this case, we have percentage, and then either S or D. And so percentage S means insert a string here, and percentage D means insert a number here. And then at the end, you make a list of the things you want to insert. So the first one is the data directory, so the path to your data, which it takes from up here. And then the second one is E, so that will be either TXX or RX one day. And then the third one is S, so that's the scenario. And so you make the name of the files like that. And then this part is reading it in and making it into a NumPy array. So it's like a Python format. And this is where I put it into the empty array that I made to kind of store it. And then I save it as a .np file. So that was CANI-SM5, the CMIP6. It's basically the same, but I loop over a list of model names instead of ensemble member numbers. And I mean, this looks a lot nicer because I didn't add comments everywhere, so it looks simpler like this. And then, yeah, your challenge is to do the bit for Miroc 6. So you can copy and paste either the CMIP6 one or the CANI-SM5 one, and then just modify it a bit. So the things you have to modify are, for example, hang on just a second, this is responding a bit slowly. Yeah, so for Miroc 6, we only have data for 2 scenarios. So you can delete 2 scenarios and you can delete the space. So there should be 2 instead of 4 in the array. And also you have to change this bit where you loop over the ensemble member numbers, because we just changed this to 1 to 51 and delete the P part to suit the way Miroc 6 is numbered. But yeah, there's the script I supplied, which has Miroc 6 in if you want to look at it, if you get stuck. And that's it. Yeah, I think that's it. So feel free to ask questions or whatever. Should I stop recording? pause the recording. Okay, right, so yeah, back to it. Oh, thank you. So I think because we finish it at 1, and I don't think we're going to manage to do everything, so we're just going to change tactic for the last hour. And I think so. I'm going to show you things, and so you guys are not going to run anything for the last bit. You can do it afterwards if you want to, but I'll just show you. I'll run some things, and we can get plots, and we can talk about them. Yeah, but before I do that, I remembered that I wanted to show you what the files that we used actually look like, the ones we used at the beginning, because, you know, I guess maybe you don't know what's in them. So just to make it more understandable what we're using, I mean, it's quite small, but I can't change it. So the first files we were using, they look like this. So basically they're files, they have like a 3D grid. It's like a map, and then I have it for each time step so I can go through. And so the first one was, well, this is 2016, and this is 2017, 2018, 2019, and so on. So that's the data we used initially. This one is TXX, so annual maximum temperature, just so you know what we were using. And then we made time series out of it. So this is an example of one of the time series that we made with the first script. It saved a whole load of time series in NC files, and then we read those into Python. So this is what we read into Python, and we saved it as an array. Yeah. Okay, and then, so the next part was to, oops, that's not the right thing, was to plot time series. So I'll run the scripts, and hopefully some time series will appear. So let me show you how this works. So yeah, this is the script for making time series. So it's script 3 plot time series.py, and it's like the other one in that you load the relevant libraries first. And then I made a switch so you can select whether you want to plot TXX or RX one day. Yeah, then we read in the time series that we saved in the previous script, and then we plot them basically. So I make a loop for the different regions. And then in this part, I'm making a figure. I'm plotting an axis on the figure. In this part, I'm plotting the time series themselves. For the different SSPs, I give them each a different color. So this is the color part. And put a title, put an X label, Y label, X ticks, X tick labels, and so on, and save the figure. And then I do the same for CMIP 6, and then there was a space for Miroc 6. So I just run this. Oh, it's already huge. That's as big as it gets, I'm afraid. So I'm not in the right place, so let me move. Okay, so it was script. I'll do the one with Miroc 6 actually. CD, I can't see. Okay, so it's this one. So I do Python -I name of the script. Oh. Okay, so my script doesn't work. Maybe I try the other one actually. Okay, so it's good I made some plots earlier because my scripts don't work. Great. Okay, so this is what we would have got if it had worked. So yes. Okay, so this is yeah, TXX for CANI-SM5 for global Europe, Balkans, and Novi. So I was just going to ask you guys what you noticed about these plots. So we have different scenarios and the different colours. But yeah, what do you notice? Like, do the scenarios
increases.
Say that again, sorry, I didn't hear.
Uncertainty increases.
Yeah, as you get to smaller spatial scales with more uncertainty, you get a wider range of temperatures. But also like how the different scenarios do you notice? Like if you look at how much they overlap for the different regions, what do you notice?
There is bigger overlap for smaller.
Yeah.
But maybe it's not a bigger overlap overall, but just a higher uncertainty, which is making these overlaps.
Yeah, that's right. So yes, when you get to small scales, generally you have more internal variability, and that makes it look like the scenarios overlap more. So yeah, when you're looking at a global mean, you have a big difference, an obvious difference between scenarios. When you're looking at a grid cell, then there's much more overlap, yes, between the scenarios, as you did.
Are these annual temperatures, like mean annual temperatures?
This is the annual maximum of the year. Yes, the TXX is annual maximum temperature. And then I plotted some other things. Oh, they're seeing the wrong view. Hang on, let me change this. Okay. So this was RX1 day. And yeah, can you tell me how temperature and RX1 day, so this is the annual maximum precipitation. What do you notice? How do they differ?
Even more uncertain.
Yeah. Yeah, so internal variability is even bigger for precipitation, and yeah, it's more dominant source of uncertainty than it is for temperature.
But the trend is not so obvious for precipitation.
Yeah, I think, yeah, that's fair too, especially the Novi said it's not really clear even what the trend is. Yes?
I think the code you need to change the units.
Yeah, because it's a bit
Yeah, I forgot to change that. Millimeters. Yeah. All right, and then I plotted the same for CICERO. So if you compare, for example, the same scenarios, so the pink one and the red one, for instance, with between CANI-SM5 and CICERO, what do you notice about the difference between the two?
It's the largest part.
Yeah. Exactly. So yeah, if we just use CANI-SM5, we might think oh, look, if I'm following SSP 585, then okay, there's really narrow range of temperatures that I might reach. But then actually, if you look at CMIP 6, you have a much bigger range. So you would be overconfident if you're only using CANI-SM. So it's worth using more than one model. That would.
But I'm confused. In CANI, yeah, that's what, this was one line graph, but in one graph I see multiple red lines. I thought it was only one line.
No, so we're plotting all 50 ensemble members for each scenario. Yeah, so there's 50 lines, 50 pink lines, 50 green, 50 orange, and CMIP 6 is 21 lines. So there's 21 different models for CMIP 6 for each scenario. Okay.
Maybe I missed the point, but what's the functional difference between these two methods or no? I mean, where you can apply one, not other, and vice versa.
I mean, so CMIP 6 is a whole load of different climate models running the same experiments. CANI-SM 5 is just one model, which is actually part of CMIP 6. I guess there's advantages and disadvantages to using one over the other. I mean, CMIP 6 is good in that it gives you a feel for how different models differ. So yeah, it gives you an idea of how much uncertainty you've got due to choice of model, like uncertainties about how to represent processes and things like that. Whereas a large ensemble like CANI-SM 5, it's maybe useful for other questions, like particularly if you're interested in internal variability, and because you can run a really big number of simulations with the same model, which allows you to quantify the internal variability well and to get its statistics well and stuff. Whereas for CMIP 6, often models just contribute one or a few members. So I don't know, they're answering different questions. I guess you can use them to answer different questions. Feel free to add stuff.
I'm just curious as to which model the hottest is that?
CANI-SM 5 is a hot model. Maybe, I don't actually remember off the top of my head.
Actually, I can see it's with CANI-SM 5, it's between 7 and 5.
Yeah.
And 7. Yeah.
Yes. Okay.
Sorry, in this lower, on the right side, this last one. Why does it have so much extremes? I think they're very random.
Yeah, I'm not sure.
They're like very distinct.
Yeah, they are. I'm not too sure why, but when you have a single grid point, it's more likely you get a lot of variability compared to if you're looking at a bigger area. I mean, they do look a bit strange. Yeah, not sure. That's the same for precipitation. I think basically it's the same point. There's more spread with CMIP 6 than there is for CANI-SM. And on this one, I was plotting MIROC 6 on top of CANI-SM. So this line and this line is MIROC 6, SSP 585 and 126, and then this is the equivalent of CANI-SM. I was just trying to demonstrate how different the two models are. Like there's two different large ensembles, but this one's a lot cooler than this one. So I guess it's the same point as on the last slide, really, that using more than one model is important. Otherwise, you think you get a false idea of how sure you are about the change. Okay, I skipped one.
Sorry, what is the start year of this?
This yeah, 2018-15.
Okay, but then we already have up to now, like 7 years to compare the real.
Yes, so I could
start with precipitation to this. So can we tell based on that which one is the best?
So we actually have more. So I didn't plot all of the data. So the data goes back to 1850. So yeah, we have loads of years that you can compare. And people do that. And then you can also do things like model weighting. So you can see which models performed best in the past and maybe you give them more weight and do like a weighted average. Well, so you have to decide how you decide which one is the best. So that's obviously a question. Like there's no set way of doing that. Some people do research into this kind of thing. Yeah, and yeah, so it's like a whole area of research to do this. It's called observational constraints, what you're talking about, like evaluating the model in the past and deciding how to decide if it's a good model or not, and seeing what effect it has on the future. Yeah, so yeah, it's something you can do.
Is it possible to calculate the error of the model and then to improve it, but not with actual changing the code and physics or the core of it, but just calculating the error?
Like a bias correction, do you mean? It sounds like bias correction. Yeah, people do that. I think Rob probably knows more about that than I do. But yeah, you can correct the model data without running it again to match better with the observational data in a statistical sense.
But that brings really another layer of uncertainty in terms of which bias correction method, which reference data, and reference data have uncertainties. So it's not 100% foolproof.
No, it's not 100% foolproof. And also you have internal variability in the observations as well. Yeah. Okay, and this one I just smoothed these ones with a 20-year moving average to get rid of some of the variability. Because often when we're talking about future changes, say in the IPCC report, you'll see things for a 20-year period, say like 2081 to 2100 or something. You don't just say, oh, this is the temperature in 2100 like that year. So just to show what happens if you smooth it. So a bit less variability, a bit more separation between the scenarios. That's it really. Too many plots. Okay, yeah, these ones are different. So here, I've made some histograms. Where should I start here? So for each ensemble member, so this is for TX for Novi. So for each of the 50 ensemble members for CANISM, I calculated the trend over the next 30 years. And then I plotted it as a histogram. So most of them are going to show warming, some of them show cooling. And then I have the different scenarios, and then I have the same for MEROC 6 and CMOC 6. And so the idea with these plots was just to look at how much does the spread change as you look at different regions like the Balkans, Europe, global. Like how does the overlap between the scenarios change? Are they more distinct or more overlapping? And also, how do the ensembles compare? Is CANISM 5 hotter than everything else? Can you tell the difference when you're on a grid cell level? Can you only see it at a global level? Those kind of questions. So anybody got any comments, observations about these?
I'm not sure I understand how you presented a trend with these bars. Like, because when you speak of trend, I would say that the trend is a line which fits somehow
results of the model.
Yes.
And then that line has some function, right? Yes. What is that, the linear function or?
Yeah, linear. So this is like the gradient. So I'm just plotting histogram of all the gradients. So each model has its own gradient, and then I put that as a histogram. So most models have, say, a gradient around, say, 0 to 0.5 in this case. Okay. And like one model has a gradient of minus 1.5 degrees per decade. That kind of thing. Okay. It's very sometimes I guess not everything comes out like so my head but doesn't come out.
But there are some trends which say that nothing will happen around 0 trends.
Yes.
So like everything is okay, it's stable.
Yeah, those trends appear when you go to a lower resolution for 1.4. In here in the global and Europe, you just have 1 for mirror. It is around 0. So as we go to the lower resolution, we get wider.
So there are not
gradients, wider
negative trends for like like everything is positive.
Yeah. Yes. Over the next 30 years. Yeah.
Yeah. There is only 1 in 6.
And move this.
The lower one. Here for the SSD 1, 2.6. There it is on 0. One line. Yes. And as we go to the lower resolution, but wider range of trends from minus 1.5 to 2.5.
That's the answer.
Yeah, the uncertainty is bigger, the smaller scale. Yes, the internal variability is more important at the scale of Novi cells than it is for the globe. And so in the global, probably this is closer to the force trend you get, like the effect of CO2. It's probably going to be reflecting that, maybe with a small contribution from internal variability, whereas this one is mostly internal variability. I mean, I suppose you still see the forced trend, like the effect of CO2 because the histogram kind of shifted like this. So yeah, and
it presents, so you can turn the histogram into likelihoods statements, which is useful. And likelihoods in the model world, of course.
Yeah.
But also it presents potentially a challenge or an opportunity to educate decision makers who have to accept there is a remote but small likelihood of approving the trend to mid-century over Novi set, which is maybe hard to get across to a lay audience when the expectation is everywhere all the time it's going to be warm, even though the models and climate variability says that cooling is still possible for sure.
Yes, indeed. Yeah. So then if it happens in real life, it's like, oh, what happens if people warming that actually it might need to be variability and then later you have an accelerated warming.
It's for these results highlight the fact that you've got to be prepared to issue those kinds of messages.
Yes. Yes, indeed. Yeah, something to be aware of. Okay. Any other comments? I'll show the next one.
Although I suppose we're unlikely to follow the lowest pathway now, given current commitments.
I'm sorry, there is a comment. Unfortunately, when the player says, I can't see the whole presentation, which graph line she's showing. Can you maybe shift the camera somehow?
Sorry. It's difficult with the hybrid.
Can we just get up the preview so I can see preview that line on
you
the
can
screen.
see it here.
Huh?
Okay. So let's okay. So
and what were you saying? Sorry, I was distracted.
That we are given current commitments, international commitments to climate emissions, there are a lot to follow in line unless something really dramatic happens soon.
Agreed. Yes.
So maybe the likelihood of a negative trend is less than we think, because we're actually nudging more toward a distribution ping pong spectrum.
Yeah, we should maybe look at the green ones.
Yeah.
Which I covered up with the blue.
But the chance of blue is vanishing small now, given where commitments are.
Indeed.
Yeah, that's a big.
Oh, there's another chat. Okay, and then nothing happened. Oh, this is the same, but for an 80-year trend. If I just change between them a few times. Anyone want to tell me what the main differences are? Yeah. Well, yeah, so yes, less relevant kind of variability. Now the scenarios are really quite separated. And that's that. And then I had the same for precipitation, which has more internal variability. Like this is really quite symmetrical, almost about zero, the name is that. And it's based with a globe that's not there. Yeah, this is all positive.
Then it's precipitation.
Yeah, this is.
Okay, can you tell me like the units of that?
Like that. Oh, yeah, sorry, I forgot to change the
so do you remember?
Millimeters per decade, I think. Okay. So like the wettest day of the year, the trend in the wettest day of the year in millimeters per decade. So yeah, it's between 0 and 2 millimeters per decade more at the global scale. And that was the same for the 80-year. So same story, narrower, maybe more overlap of scenarios than was for temperature, I think. Okay, and then there's the last, these ones. So for this, this is showing, so I have TXX on this side, so that's the hottest day of the year. TNN on this side, this is the coldest night of the year. And then on the top row, it's both, let me, okay. So I calculate the trend for each grid point for the next 30 years, and I pick the ensemble member which has the smallest trend over Europe as a whole, like the European mean. So this one has the smallest trend. This one has the biggest trend. And then this is the same for the 80-year period. And this is the same for TNN. And it was just to show how different ensemble members can be. Although actually this didn't look quite as I thought it would. I thought it would look like this. But it looks like this. I think this one has an area of cooling over the ocean and then a big warming here, whereas this one's a bit more evenly spread. And then the other thing was that as you look at an 80-year time period, then these two look much more similar to each other. And again, it's this internal variability thing. And I think, so TNN is looking more like how I expected it to look. So this ensemble member actually shows a cooling over part of Europe. And this one shows a strong warming over all of Europe. And again, when you look at an 80-year time scale, it's more similar between the two. This is the Canny SM5, I think I forgot to say that. So the Canny SM5 large ensemble SSP 585. So the one with the most warming. Yes, I think I said everything. I don't know if anybody else has any other comments.
I have a question.
Yeah.
Let's say that if we had like nuclear war in the next 10 years, so would you be able now to include some parameters to explain what the temperature would be like?
Yeah, it's possible to do that, and I think some people have done that.
Yeah.
In the past. I've seen some papers simulating a nuclear winter,
Yes.
or whatever. I think you just change like the forcing age. I don't know how exactly you do it for nuclear. Is it aerosol? Okay, yeah, change the aerosols. I've also seen, because it has some parallels to volcanic eruptions, like a big volcanic eruption produces sulfate aerosols which reflect sunlight and cause a cooling. So I think it's the same kind of thing, and yes, some people have simulated that. I don't know too much about what the results were. I haven't really looked into the literature.
I wonder, why does the minimal night temperature for different models, maximum and minimum scenario situation, why is there a bigger difference in the minimum compared to the maximum day temperature in the left side of the image?
I mean, it could be, so I'm kind of like making this up as I'm going on, but it could be because in winter the temperature is more kind of affected by like large scale weather systems coming through. There's generally more variability in temperature in winter than there is in summer, I think. And in summer, I think it's just the processes are different in summer than they are in winter. Rob, do you have a better answer?
It seems okay.
Yeah.
In winter there is more land circulation, maybe, so
more atmospheric, like more, like say depressions, like extratropical cyclones and stuff going through in winter.
Land is more heterogeneous, something like that. Is that the reason for forming these more rapidly changing weather systems?
I'm not sure I totally followed.
No.
I mean, the maximum trend could include the effect by land surface speed. So the soil moisture content is really important in generating high temperatures and climate model simulation. So what would be interesting to see is how the precipitation with the soil moisture changes in these different ones, the extent to which there's a large, strong land surface feedback that generates the TXX.
Yeah, I agree. Yes.
Thank you.
And often heat waves are associated with blocking anticyclones as well. So you have actually, well, probably multiple processes. Like you have the anticyclone which stays in one place in like clear weather and incoming solar radiation, heating things up, and then you have the land surface feedback as well. If it's dry, particularly, then it gets hotter. And then I just have one more slide just for the precipitation. For the annual maximum precipitation. And it's a lot more, you can see it's a lot more spotty. Like, yeah, and yeah, some places you have drying in this one. And so for this one, I took the one with the least increase in rain and the most increases. Yeah, obviously not warming. And here they're much more similar to each other. So there's a small increase everywhere, well, apart from the Mediterranean.
What are the ensembles here?
This is Canny SM5.
There's one the one model, 25 runs, 50 runs.
50 runs, yeah. Picking the one with the biggest and smallest trend over Europe. And this is SSP 5 like no particular reason for choosing that one. I don't know. I just kind of autopilot program SSP 5. You look like you're thinking wrong.
I'm still trying to figure out why there's 4. Can you explain why there's 4 panels?
Oh, yeah, sorry. This is next 30 years, so next 80 years.
Okay. Oh, I see. Yeah.
Smallest trend, or most negative trend, most positive trend, and the same.
The difference between minimum and maximum trends is lower for the larger periods.
Yes. And I realized that isn't the last slide. I also had it for the Balkans, but I think the story is the same.
The longer the period, the smaller the change. The difference between.
And here you have a more obvious difference between these two when we did the European step. And then I just have creases. And that's it. Yeah, so that's everything I have. So I'm happy to try and answer questions or whatever, but yeah, it's just, this was a topic I found interesting, this whole idea of uncertainty and spread and where does it come from, and like when does internal variability matter and how much effect can it have? Like I remember reading, so kind of like the paper I showed you in the other presentation. I was quite surprised actually how much effect internal variability can have. So it kind of stuck with me, really. Yeah, this one.
Okay. Yeah, that was really thought of the paper.
Yeah.
We just see.
Yeah, that kind of stuck with me.
So whenever we use models, we should use more than one model.
Yes.
And then see what's going on. Not to jump to conclusions.
And use multiple ensemble methods.
Yeah.
Yeah. And also for interpreting the observational record as well. It's useful to bear in mind that we also have internal variability in the observations, because sometimes I see, people are like, oh, for the last 30 years, precipitation increased in this location, but 30 years is actually quite short time period for looking at trends, and so it can, because people automatically go, oh, global warming has caused this trend I see at this grid point over the last 30 years, but it might be that it's a variability thing. So it's, yeah, just something to be aware of. So, done. There's some messages on the chat. Is it old?
Just saying thank you.
Oh, okay.
Well, thank you. I don't know if I heard that correctly or something like that, but in one lecture, 2 or 3 years ago, I was introduced to the concept that there is in the North Atlantic Ocean,
yes.
Which is actually cooling.
Yes.
And when I asked why is that happening, yes. The professors didn't have the exact answer.
I agree.
So maybe in these few years the situation has improved the knowledge of that. Something about Gulf Stream, maybe,
I wonder if there's a lot of the models and the observations are detecting this influx of null water from Greenland, and the melting of Greenland is affecting the whole North Atlantic circulation. So you've got both the influx of fresh water affecting the circulation and the actual water in the freshwater temperature itself. But, that's all I can really say on that.
Yeah, I can't say much about it off the top of my head, but I've heard of it as well.
Yeah. I'm wondering if that maybe if that not water can result in some kind of Gulf Stream shutdown, like in young grass.
Well, that's the fear that if you have too much fresh water, the Gulf Stream all depends on turning over water to different density. You put lots of cool fresh water into that system and it's so potentially can slow it down. I think my understanding is that that's thought to be unlikely this century, but there's already evidence that the strictly flux is slowing. There is evidence that the demand is slowing down. So a complete shutdown is thought likely still to be unlikely this century. But there are applications where you have to look beyond the central time and developing coastal infrastructure that can be there for beyond 2100. It's susceptible to sea level rise, and that's one of the things you have to factor into the calculations. Possible shutdown, because that changes sea level as well. Interesting. Yeah.
I don't have anything to add.
Something else. So thank you very much for enthusiastic and asking questions. Thank you, Carley, for this, for showing us how we can view the scripts and look into different ensemble members and different models and try to find what we wanted to see. So thank you very much for this. And if there is no other questions, I would like to say bye-bye, see you tomorrow.
Okay, yeah, thank you for being a great audience.